Okay, I think we're on as far as the recording goes. So welcome everyone to TAOCP number 2. This is, as the number suggests, our second meetup. We are working our way through The Art of Computer Programming by Donald Knuth. And our first meetup was essentially just an introduction to the meetup itself. We did read a little bit of some preface and a couple of other early sections from the first volume, but it's really today that we're going to start the real content, and that's the section on algorithms from the first volume, and we should start in a couple of minutes. I've asked people to enter their responses to this question in the chat, and so we should be able to see what people say. So Akash says proving correctness. Yeah. Yeah, both of those things, proving and correctness, they're like independently difficult. William is asking, does anyone have a good online copy or PDF for TAOCP? I read through a lot of it in college, but I'm home now without the library. Yeah, so, like the official publication channels exist for the online versions. O'Reilly has them available, and I think that there's a couple of other publishers that do offer PDF versions. But if you do a Google search, you should be able to find things. If anyone wants to give a link, that's fine. But it's not difficult. Jason says, having intuition about the correct algorithm for a given task. Yeah, wow, that is, yeah, I think like if we had like the secret sauce to that, that would be really nice. Yeah, Michael also suggested O'Reilly, in case you have a subscription, that's really convenient. The only thing with O'Reilly is that, as somebody mentioned the last time, they don't seem to have the page numbers, which makes it a little annoying in terms of references. But yeah, it's a pretty good quality otherwise. Arthur says, I was going to say I often find it hard to imagine coming up with a new algorithm in the sense of binary search tree or quicksort or priority heap or whatever. But on more reflection, I think I disagree with myself. Okay, well, let us know when you settle the debate. What's the alternative? Like, if you disagree, then what is the other thing that is conflicting?
Well, in the sense of having a toolbox of algorithms, where you can name algorithms and select one, or maybe even put them together, and say, this calls for a linked list, and then we're going to merge them doing this trick, but it seems like putting together things from an existing toolbox. Okay. And the toolbox came from somewhere, right? In the time period we're talking about with Knuth, in the 50s and 60s, inventing this stuff, it's like, whoa, that's crazy.
Yeah, it is crazy. Yeah.
But on the other hand, then I think about, like quicksort, you just break it down, right? Binary search, you just, obviously, it's either in the first half or the second half. You think, So maybe it's all obvious. Maybe it's just they got the obvious stuff first, A lot of computer science is like that, where the really foundational stuff is like, oh yeah, of course you do it that way. I think it was harder in the 50s when you also had to struggle with the machine. We've solved a lot of the ergonomics problems in the intervening century.
Yeah, those are great points. I did get a prompt for somebody to join, but then before I could respond, it disappeared. I'm not sure what that means. Whether Google Meet somehow hid it. Oh, there we go. Here, I think I just have to jump on it quickly.
They probably closed their browser tab, I would
What's
guess.
that?
They probably closed the tab.
Yeah, it's possible that they just disconnected, but it was a little disturbing for me. Like I need to be on top of this. Um, but yeah, so yeah, all great. I think Arthur, your response is similar to what let's see, Jason is sort of saying, right? Like having intuition about the correct algorithm for a given task. Is that fair to say?
I think that's a big part of one's job as a programmer is to have that toolbox and to use it. But to use the toolbox analogy, it's like you have to know whether to use a hammer or a screwdriver. But can you
Hmm.
imagine like the guy who came up with the idea of a screwdriver? Like that's a little mind blowing, and
Yeah.
that's what I was trying to get at there. Like, how does one do that? Um,
Yeah.
but maybe if you don't have a screwdriver and you just think about it a little bit, you're like, oh yeah, that would work. I should
Yeah.
just make that.
I think for me, it's generally breaking down a problem. It's sort of like you have this sense of some solution, um, but then how do you turn it into this algorithmic expression where things are sufficiently precise and granular enough to turn it into or to be valid as an algorithm, which obviously we're going to read about today. But that's one of the more difficult things I find. But yeah, there isn't one, but I just asked for one. So very nice. So here's the agenda for today. We are going to read through a few pages of this section 1.1 from volume 1, Fundamental Algorithms, chapter 1, till about 3 p.m. And we'll take a 10-minute break at that point, and then we'll come back. The meet will stay online, recording will go on. When we come back, we'll do some exercises and just talk about other topics, and I'll go over the next meetup as well. So the system that we have is we will read a page or two at a time. I'll put up a slide saying how much time we have. It's just basically enough to read the thing and maybe understand it a little bit if you haven't read it before. But then I'm hoping that we'll have some discussion and things can be sort of fleshed out, and you are encouraged to enter your thoughts and ideas in the chat or the shared document that I did send a link to earlier yesterday. And so here's a little slide explaining that process. And let me actually paste the link again here. So, if you have something that's a little longer or you just want to keep it around so that it's visible to you the whole time, you can enter it into the shared doc. But the chat actually works really well, and I'm going to copy all of the chat responses and comments into this document, and after a while, I'll just post it to the Meetup repo, and all those links are available. I haven't managed to actually post the notes from the last meetup because the chat actually comes out sort of unformatted when I copy it, and I need to sort of make it nicer for Markdown. I just haven't had time to do that. And also, one mistake I made was I closed the Meet window before copying the entire chat. So I missed probably a good 20, 25, 30 comments, but I do have the earlier ones. If somebody has like the last 40 or 50 comments, if you could, send those to me or just let me know that you have those available, then I can, or just put a pull request when I actually post the document. So we will now start with this quote from Donald Knuth. And I just felt that this sort of sums up, what his sort of idea was behind however he presents algorithms. It's sort of this thing that, you just have to get into the details that a lot of people find unpleasant. So, with that, let's begin. So if you could spend about 3 minutes on the first couple of pages. I've also pasted a couple of snippets from the beginning of our reading and the end of our reading. So this is from page 1 through page 2. And this is just very straightforward stuff, mostly historical. And if you could just read through that, and at the end of 3 minutes, then we'll discuss it.
So again, don't get into the actual.
Sorry. Does anyone need more time? Okay, so what are your thoughts? Enter it into the chat or speak up.
It really feels like Knuth is just talking about the essence of an algorithm just being like a recipe, a series of steps for computation, and some of its historical basis.
Yeah, I think that's a pretty good summary of the entire section. What did you think of the historical summary? Is this something that you were familiar with, like in general terms, or are there things that you learned? Anyone want to volunteer?
One thing that I noticed, which of course is going down a completely pedantic rabbit hole, but you can tell that Tech is very good at typesetting Latin text and very bad at typesetting Arabic text. Knuth is very detail-oriented, very pedantic about, giving everyone's middle name in the index and so on. But he doesn't even try to do the Arabic.
I think he does have some Arabic somewhere. I remember seeing some Arabic. I don't
Actually,
remember
probably
what the
in
context
index,
was, but yeah, yeah. Knuth is very detail oriented, so he's like really obsessed with very, very fine details. And, I did enter into my notes that it's sort of like if you just collect all the historical information, that could be a little book of its own. And what I found the most interesting was there was a lot of things that I didn't know. I didn't know about the algorithm to algorithm corruption and sort of the transformation. But the Ada quote at the beginning of the section, did anyone read that? I don't know if people were interested in the quotes, but that just sort of blew me away that this person, like when there wasn't even this electronic computer and applications, she was able to, sort of uh, guess at what this could be used for. But yeah, nice. Okay, so let's move on to the next couple of pages. So continuing on page 2, and then through page 4, there's a little snippet over there on the slide that you can stop at. And this is a bit longer, so we'll have about 7 minutes till about 2:30. Okay, so we just read like the first algorithm that Knuth is using as a model to sort of introduce notation, Euclid's algorithm. And so he's sort of laid down algorithms will have a name, there's a format that is very precise, and there's some operations and operators that he introduces. Arthur brings up a very interesting point about the chaining notation and I didn't even really think of that because that's sort of like now it's just expected in many languages. But yeah, like at that time, that would be an interesting question if Fortran, for example, had that in its initial version. But any other thoughts or questions about clarifications about any of the notation or the format? Akash is asking. By the way, Akash, feel free to, when we're discussing, you can speak up. But yeah, I mean, chat is fine too. I mean, chat is
Yeah.
great while we're reading because then we're not interrupting people. But when we're discussing, yeah, please speak up. So he's asking if we prefer CLRS or Knuth. Being familiar with CLRS, this definitely feels weird. Well, everything about Knuth will feel weird. I think that's a common reaction just because he's taken a very specific point of view and he has his own he's mastered his own notation and programming style and language. CLRS, if you could maybe clarify what you're referring to.
Yeah, the CLRS is the Introduction to Algorithms book by Corman, Levinstein, Rivest, and I can't remember what S stands
Okay,
for, but yeah,
sure.
that is like a seminal book which I used for during my master's in the algorithms class. So it definitely has more mathematical approach as compared to the programmatic approach that I think Knuth uses. I haven't read through Knuth, but yeah.
So which notation are you suggesting is more or less mathematical in what we just read? Like
So Knuth,
the pseudocode, sort of the arrow notation, or
yeah.
something else?
So the Knuth notation is definitely like less mathematical than CLRS, but I guess it just has to do with getting used to it and getting familiar with this notation once you're reading through the book.
Okay.
So yeah.
Okay. Yeah. Yeah. I've actually used CLRS as well, long time back. I don't remember the notation anymore. So, but that's an interesting thing, like how different texts just have their conventions, and Knuth again is very, very special. Yeah, anything else? Anything about his choice for the first algorithm to present, Euclid's algorithm? Would you have chosen something else?
Also on the CLRS thing, I'm not familiar with it, but I just Googled a pirated copy over here. And the CLRS notation for the algorithms is much more algol-ish, like very structured programming. It has like while true, repeat until. It has if, then, else on separate lines. You know, if this condition, then do a thing, else do another thing. And really only incidentally then numbers the steps, right? It's not like you do step 1, then step 2, then step 3. It's just like, well, you just go. And if there's a while loop, you know that you go back to the beginning. I want to say that Knuth was a bigger fan of GoTo than the people who wrote the CLRS book.
Does
Actually,
CLRS
right?
has an actual, does it use an actual programming language for code as well, or it's just the pseudocode?
It's just pseudocode, I think.
Okay,
Like I don't
I
think
wonder
there
if
is any.
that's one reason, because Knuth, at
Mhm.
least in the first volumes, will often present a program, in his assembly language, and I think the fact that he chose assembly language and then, he's got the algorithm also in some pseudocode, I think maybe he's sort of mapping between the two to make it sort of easier for us to follow the correspondence. And because it is assembly, the style obviously is not going to be as structured as some higher level pseudocode. But that's just speculation on my part.
His assembly language is going to use essentially GoTo, so I guess that makes sense that he would want to stick with that.
Yeah, could I ask why did it's in my admittedly pretty long experience that these if else conditional expressions on separate lines, and then first of all, while true is not very common at all, but I mean you seem to like think that they're usually on the same line, or that they're usually in some sort of I don't know, ternary form, with Elvis operators or something. Is that?
Are you asking about CLRS? Because I think that the while true, the while and the if else was in reference to CLRS notation, which we can't see right now. But
there was somebody who talked about something like it seems very algol-ish, where you have these statements on separate lines.
That's Arthur, so he can respond.
Yeah, in the CLRS copy I was looking at, it had like pseudocode like if, and it would bold all the keywords. Of course, we bold all the keywords because they're the most important part of the program, right? So if some expression, and then it would have another line, right? Line 11 says if A greater than B. Line 12 says then, set A equal to B, else set B equal to A, whatever. I guess if you're coming from like a BASIC or Fortran, you might be more used to more Knuth style of saying, on this step, if this condition, then do something. And if you needed to do multiple things, you would say, if this, then jump to that, jump to a subroutine or jump to later in the code. And it would be very short. And so it would just be and there's no else, right? It's just, if this is true, do that. Otherwise, I'll tell you what to do later. Which is a less structured way. You don't have blocks of code. I guess the thing I was looking at didn't really have blocks either, but it still sort of laid them out as 3 lines instead of just a single line of do something, but conditionally, right, with an if in front of it. It's really laid out as this is a control structure of if a thing, then, and then sort of recursively 2 other things, the then and the yes.
So James is still holding up a page from CLRS, and I had a look at it, and you can just click on James's thumbnail, and there's a pin button there, so it'll zoom it up for you to see.
No, I'm using both hands to hold it up, so I can't actually do that. So can you tell me if it needs to do anything to make it look better?
I think it looks fine. So yeah, I think I had a good look at it. So yeah, thanks for the visual. By the way, I think in the last meetup I was talking about this text about numerical analysis. That's a very, very famous and established reference. And I think James had found a copy. It's Numerical Recipes. Is that right, James? You had held up a copy of numerical.
I think so.
Okay, yeah, I turned away. But when I was watching the video later on, I saw like a little glimpse of Numerical Recipes. But yeah, it is a great book. The only thing I don't like about that book is, if I remember correctly, all the code is copyright and trademark and patented, and so you can't actually use it for anything practical. So at least not without paying them, I suppose. So yeah, so let's move on.
Also found a fun fact that for the camera to work in Google Meetup, the phone has to be held upright. So I tried like turning it down like that to show the book. It shut off. So it's like
Okay, good to know.
So like, the book is upright on my lap, and so I'm putting it back to me. I'm putting the book down.
All right. Okay, so let's move on to, this is again just a little piece on page 4, introducing like how you can work with algorithms. So we'll have about 3 minutes. Okay, so the intent here was really just to clarify things by allowing people to work things out on their own, so they can kind of have a chance to see what Knuth actually means by this notation. So very straightforward stuff, but in case anyone had any questions, we can go over it.
Well, I thought it was interesting that when I read the algorithm in the previous section, my first thought was, I need some paper to try that out. And I thought it was funny. It's like, okay, next section, he says exactly that.
Exactly that. Yeah. So, I think you are thinking alike, and that's really a great sign in a book, right? If you're anticipating what the author is going to write about. Okay, very nice. So, yeah, go ahead.
If you thought you needed a piece of paper to work it out, did it actually help to read someone else work it out? Or did you still feel after reading that paragraph like, okay, I kind of get it, but I want to do it myself?
How many people actually worked it out? As opposed to just reading it and saying, yeah, I know what this is now doing.
So if I did it on paper, I'd probably use smaller numbers. So I'd probably use like,
Any other
13,
person who actually worked this out on paper and pencil?
That's on my list to do after this session.
If there were, how would they signal it? I don't think we have a raise hands here, do we?
We don't have a raise hand, so you can just speak up or raise your hand. We can pretty much see everyone or enter it into the chat. Anyway, so that's fine. Yeah, let's go on. This is sort of the meat of the section, and so we'll have about 7 minutes pages 4 through 6 till about 250. Does anyone need a minute or two more?
I do.
Okay, so we just went over a couple of things. There is a comparison to some more commonly used analogies like a recipe uh, uh, compared to an algorithm. And then there's, of course, the 5 key features that he mentions that really an algorithm must have. Finiteness, definiteness, input, output, and effectiveness. First of all, any questions or things you wanted to clarify or sort of flesh out, and then any other comments?
Well, I was curious about on inputs. It says an algorithm has 0 or more inputs. And I'm trying to think of an algorithm that can have 0 inputs.
That's a really great question.
Generating a random number has 0 inputs.
Well, a random number, like a random number generator, will still have a seed.
Seed, yeah.
Which is an input.
An algorithm for computing pi. Now you could say, well, it makes sense to give it an input of like how many digits do you want or something like that. And if it goes forever, it's not an algorithm. But I think you could imagine an algorithm for computing a specific constant in some way.
But then it's still having certain inputs, they're fixed, but it's still, taking some fixed numbers and putting it into an algorithm to come up with a fixed answer.
Well, I think that's playing semantics, though, isn't it? I mean, you can imagine parameterizing anything. Even the value you're trying to compute, you could say, well, this is an algorithm for computing any number. I just happen to plug in pi. You want to compute e, you just do this to it.
Yeah, I think that is a tricky question. Like, is an algorithm for computing pi, is pi the input in some sense? That there is some computational method for, irrational numbers, and for pi, it works this way. If x equals pi, apply the, pi calculation. If x equals e, apply the e cal. But yeah, I think that he's just being a little flexible here. He's just saying that, yeah, there could be things that are hard-coded in some sense, but we still want to call them algorithms because they do satisfy all these other properties. That's my feeling.
Okay.
Anything else? The x hard-coded to x and y. Yeah. What did you think about, so input and output to me, I thought were pretty obvious until James pointed this out. But the other three, I guess finiteness to me was also, yeah, pretty obvious that there needs to be, some termination. Otherwise, is it really an algorithm? And he makes the distinction by calling something that is not going to terminate a computational method. But okay, that's fine. But effectiveness and definiteness, those are a little vague in my mind. Would anyone mind, giving their take on those two? Like, how did you understand those two features?
I would say that effectiveness is a way of phrasing the very fundamental idea of like CS 101 idea of an algorithm of breaking things down, divide and conquer. If you don't know how to get from here to here, do you know how to get halfway? Write that part down, then worry about the other part. And effectiveness in his model seems to be the same idea of break things down into steps that are small enough you can do them effectively, whatever that means. But he gives some examples of steps that are too big.
I think that's a great word. That the operations need to be, you need to be able to perform them effectively. And how do you know that? Like, you say, like go from point A to point B. Like, how do you do that, right? Are you going to drive? Are you going, like, there needs to be a very, but what's the difference between effectiveness and definiteness?
Well, I think definiteness is just how carefully it's explained.
Mm-hmm.
Effectiveness is, does it work? And you can, like, very clearly explain something which doesn't work.
Could you give an example of that?
Well, let's see. Calculating pi, return 4. Very clearly explained, definitely wrong.
But I don't think that that's what he means by effectiveness. Like, I definitely understand where you're coming from here, especially in a programming context. But when he says effectiveness and the way he explains it, he's not really talking about whether it works or efficiency or any of these programming ideas. He's really talking about, like, does it ask the reader to do anything that the reader is going to find difficult? Mm-hmm. So I think it's possible to be definite but not effective. But I'm not sure that it's possible to be effective without being definite.
Okay, Jason says perhaps it would be possible to define an ineffective algorithm. Well, his definition includes effectiveness. So are you saying if we take out effectiveness, then some process that you've defined would not be an algorithm? So Michael says an algorithm is effective if you can do it. It's not effective if there's no way to do it or if there is no reasonable way to do it. But how is that? Why does he distinguish effectiveness and definiteness? Do these really need to be separate features? Knuth would say that you can solve any problem in NP definitely, but not effectively. Okay, so it's non-polynomial time. There is a solution. So we'll definitely have, but isn't that effective either? I mean, like, even if it's NP, it's just going to take a very long time. And you may still have very effective operations that you are definitely carrying out in a very precise sequence.
Oh, yes. What I meant, I guess, was it's possible to define a very short, fast, definite algorithm for solving an NP problem, like the knapsack problem, right? Find a set of these blocks that all fit into the knapsack in the best possible, or exactly, right? Forget best possible, because then you have to compare things, and that's slow. But the way you would do it is like you would get an oracle for doing it, and the oracle would put the blocks into the knapsack and show, look, here is the knapsack, it's full, that is definitely a solution. Like, this algorithm always works. The oracle gives you the solution, and it's a solution, and you're done.
Mm-hmm.
But that's not effective because I, as a reader with pencil and paper, can't implement it. I don't actually know how to construct that oracle. If I had one, it would definitely give me the answer. But it's not effective in the sense of Knuth 0.5.
Okay.
And again, I think that if you had an algorithm that was just try every possible combination exponential number of times, it'll take billions of years, but it'll get done, I think he would call that both definite and effective. It's not very efficient. It's very tedious. But I think it's effective in the sense of his 0.5. He's using it in a way that is not the colloquial way that we would call an algorithm effective or efficient these days.
Okay. Michael says he thinks a definite algorithm is one where all the steps are correctly defined. If there are corner cases, then there are some inputs where the algorithm doesn't work and it is not definite. Corner cases where the steps don't work or cannot be applied. Okay. Yeah, I mean, I kind of get it, but there seems to be some overlap in. I think it's really the general term is getting in the way of sort of my understanding at least. So okay. Michael continues, I guess I should say where all the steps are not completely defined. So then that would not completely define. So does that mean it violates the effectiveness, or does that mean it violates the definiteness? It's a question for Michael. Or both. Definiteness. Okay. All right. Let's just quickly go through this next section, which is really just sort of comparison. So I'll give about 4 or 5 minutes for this. Okay, let's take a break, 10-minute break, and when we come back, we can continue the discussion on what we just read. And then there's one little piece that has the mathematical definition, which is also kind of interesting. So please feel free to turn off your cameras and just chill out for 10 minutes. We shall return at 3:15. All right, we are back. Yeah, so let's discuss what we just read. That was pages 6 through 7. And he essentially compares the concept of algorithm with cookbook recipes and remarks on finiteness requirements may not be practical enough. In practice, we want good algorithms. And he gives some elucidating examples using Euclid's algorithm. So I see some comments during the break. Arthur is wondering if Knuth uses the notion of types. And Jason points out the example that Knuth has given of Euclid's algorithm. If 4 is the largest integer as applied to, I guess, Fermat's last theorem, or this is some other formulation as an ineffective operation because the algorithm to compute that isn't defined. And Arthur says, Arthur, do you want to just explain your comment?
Sure. I just keep harping on this as we keep debating what exactly does he mean by all of these things, and do they overlap, and did he mean overlap? Basically, I'm seeing the effectiveness criterion as meaning, do I, the reader, know how to do it? Right? I know what you're asking because it's definite. That's taken care of, but can I do it? Or am I like, I have no idea how to do this? Whereas the definiteness is like, do I understand what you're asking? Like whether I can do it or not is irrelevant, and maybe I can't even tell whether I can do it because I have no idea what the algorithm is asking me to do. And so that's similar to the P versus NP distinction, right? Something is NP if I can actually do it in polynomial time, but it's an NP if I can at least detect that I'm doing it right in polynomial time. I may not quite know how to do it, but at least I can tell when I'm doing it right.
What about the comparison with the cookbook recipe? And he tries to explain those features.
That paragraph sounded remarkably like a conversation I had with my mother right after I moved to it. And she tried to explain to me how to make tomato sauce. And I was saying, no. I need quantities and definitions.
I think modern cookbooks are actually a little more specific than they were back then, too.
Okay, great. So let's go on to.
So before we move on, I found one interesting thing. I'm reading the second edition, and I think everyone else is reading the third edition.
Yeah.
So when I first went looking through it to find out where I stop, I couldn't find that line, the effectiveness of computational method. Turns out that in the second edition, there's another sentence after that, which apparently got deleted, which I thought was kind of interesting. The line is, such theories is not investigated deeply in this set of books, although will be considered briefly in chapter 11. So apparently we reconsidered chapter 11 after that.
That's some ways off, yeah. All right, so this is our last section that we're reading, pages 7 through 9. Anyone need another minute? Okay, so we just read about this formal definition of an algorithm and computational method. So it's like purely mathematical expressions. And then he also does introduce this concept of effectiveness to that definition using a finite encoding, which I was calling the Markov strings, but I'm not sure what the right technical term is. Anyway, so any questions?
This is certainly the place where my eyes start to glaze over if I don't catch myself, where I'll just skip over all the math or math-looking stuff and had to go back and say, no, we're here to read this thing. I should read it.
This is your chance, even though it's just 5 minutes.
Yeah.
So, like whatever amount of time you give is probably going to be inadequate. But, did anyone get anything from those couple of paragraphs?
Yeah.
Something else that I would say is possibly helpful here when you're reading these is he chose his variable names not completely at random, and he doesn't say it. But as soon as you realize that I stands for input and omega stands for output, like it gets a lot easier to understand what he's talking about. So I think I will be looking for and encourage people to look for that sort of pun, in other places where the math gets heavy. Try to figure out what these variables represent. He doesn't seem to want to tell you that straight out.
Yeah, okay, so let's just go over those variables. So he says, right, so there are these 4 variables, a quadruple. There's Q, there's I, there's omega, and there's F. I was trying to map them to the 5 features. Like, he's given sort of a layman, everyday explanation, or almost a definition, you could say, because it is precise, but it's using everyday terms of an algorithm. And then he gives this mathematical formulation. Does anyone want to have a stab at mapping those 5 features to these variables or these terms, the mathematical terms? Not even input and output. So, yeah, I mean, that's pretty straightforward, right? Like, where does definiteness, effectiveness, and what's the other one?
Finiteness.
Finiteness. Okay, so where do these show up in the mathematical definition?
I would say that f being the function that takes you from one state to another is represented, sort of represents the definiteness property, but also effective. I mean, the whole thing is kind of effectiveness, and finiteness is just explained in English after the fact. Right? The sentence is about, we say it terminates in k steps if.
You're right, at least in the initial definition, initial couple of paragraphs, but then he goes on to actually address the finiteness in very precise mathematical terms. Did anyone get that? Jason asks a great question. What is Q supposed to be? Others make sense, but I don't quite understand what Q is. And I think that's the question that everybody in America has. But we will focus on Knuth. So what is Q?
Yeah, as far as what it stands for, I don't know. But yeah, it's the state of all possible inputs, outputs, and other machine states. Where here the inputs and outputs don't really mean the numbers that come in or go out. It means the state the whole machine is in when you put in the input, and the state the whole machine is in when it produces its output, and everything in between has its own sort of state that's represented as this tuple of numbers. And he allows the machine to get bigger and smaller too. Right? Sometimes there's just a pair of numbers, there are other times there's 4 numbers.
Michael says Q is the state of the machine, and Miguel says question mark Q is I plus omega. Input and the union of the input and the output, but it seems like it's more than that, right? I mean, he's clearly including some other stuff in there. How about the Euclid algorithm expressed in those mathematical terms? Could somebody try to explain? Maybe I think that's a more concrete way to understand the mathematical definition. That's on page 8. You know, the set of equations that's marked 2, so that area. And then he says the correspondence between this notation and the algorithm E is evident. So he's actually suffering from the same thing he was complaining about, you know, exercises left to the reader or something like that. But yeah, so anyone want to explain that section, that paragraph?
So it seems like a regular pattern matching, like a la Haskell, right? Like if you only have m and n par, that function will produce a quadruple m and n 0 and 1, right? So the numbers seems to be like some sort of tag. If what you have as an input is an m and n some number and 1, then you want that function will return the quadruple m and n, the remainder, and 2, and then so that means that output can only be fed to the next step, and the last step it will goes back to the first step. So I guess at some point it becomes so it's basically the same thing as before. Like each step returns an output, like a typed sort of an output that can only be fed to the specific step. Right? That's what I
Okay, so
see.
you mentioned steps.
Yeah,
So
I'm
there's
tidying it.
obviously
I'm tidying it up to the actual description of the algorithm.
right. So that's great. I think that's a really great parallel that you're drawing. So there were steps in the algorithm, and they're clearly labeled and numbered. And then you can see here, there's these four, well, actually five equations, because the first one actually has two equations, right? Page 8, we're looking at this, the mapping that he's defined. So how do these correspond to those steps in algorithm E?
I don't think it's one to. I don't think it's 1-to-1. It's just that what I see, for example, so the first function, the first step of the equation, initialize the whole thing, right? So you have just two random numbers, and you get the first quadruple.
Okay, so let's take that. Where in the mathematics is that first initialization expressed?
You mean in the algorithm?
No, there's the algorithm, and I'm trying to reconcile the algorithm and the labeled steps in the algorithm. There was E1, E2, E3 with these five equations. So is there, as you said, it may not be a one-to-one correspondence, but where is that? Where is that first, E1?
Right, so step E1, the find a remainder step, is that second line of the equations, the one where the trailing number is 1. Right? The fourth number in the tuple basically corresponds to the step of the algorithm. Right? Step E2 is line number 2, E3 is line number 3.
Okay, so that the fourth entry or the fourth slot of the quadruple is representing the steps. So if we had like a 10-step algorithm, we may have like 10 mappings or 10, sort of these equations that are showing what the transition is going to be. Okay, so that's great. What about the other stuff in the mathematical set of equations? Or let's look at like E. So what would E2 be? E2 is, if we go back to the actual step, that is, he has a name also, right? Is it 0?
It's literally 2, right?
So how is that step 2?
I mean, the function, right? The function that takes as an input a quadruple that has the index 2, its result is either, if R is 0, so it's basically it's E2, right? So it's basically it says for each E something, the index of the tuple is basically itself. Like E3 is basically the reduce. So the last step is the substitution and calling again the algorithm from the beginning.
Okay, so this is like a discretization of this function. It's defined in these 5 separate pieces. And each piece roughly corresponds to one of our algorithm steps, right? And that's why he's used that 1, 2, and 3. So the piece that has the 2 in the fourth slot, line number 3 in the set of equations, that's the case when the remainder is 0. He's saying, if the remainder is 0, then the function is defined this way. What you do is you take whatever quadruple you had, and the return or the result is just the singleton n. Does that make sense to everyone? When the remainder is 0, the output should just be n.
Yeah, and that matches to the pointwise thing that he said that omegas have to have, right? Like if you feed n, it returns n again. So you stay in the same place you were as part of the.
Right. Is that right?
Like,
is that the fixed point requirement on line 3, or is it somewhere else?
Sorry, what?
Repeat the question.
You mentioned the fixed point requirement. The fixed point
Yes.
requirement being that, if you apply that function f, whatever it is, in this case, he's defined it for Euclid's algorithm. He's saying if you apply it to the set of outputs, you should always get back the same value.
Mm-hmm, same output.
So where is that expressed in these equations?
I see it in the first step.
Okay. The
Like
second
if
equation.
fn is, yeah. Oh, yeah. First, second equation of the first line.
For the first line, right,
Yeah.
right. Yeah. And the remainder is the third slot, right, in the quadruple. And there, it isn't there in the first two because that's sort of like, yeah. How would we explain those first two equations? Do they correspond in any way to the written pseudocode algorithm? Or in terms of the 5 features?
I missed the question.
I'm trying to find a correspondence between each one of these mathematical equations or mapping entries with, what we've read before.
So in the
Mhm.
I think that one goes to E0, which I'm trying to find. But, like, that one he listed a bit later.
E0 is not part of this particular quadruple. But you could add a line to equation 2. It would be something like, I'll write it in the chat.
I think that may be one of the exercises, if I remember. All right, so let me just go over the chat comments. Michael says Q is even much bigger than that, meaning it's bigger than just the input and the output and the intermediate states. And okay, so that was just clarifying what Akash was saying. And Jason says f of q should equal q for all elements q of omega, input and output. No, omega is just the output. So it's the set of values that comprise the output. And so he's placing this fixed point requirement on all of those values.
Omega is the end result. So omega is the end.
Omega is the end, exactly. Yeah.
Omega is
I
the
mean-
set of- the set of all possible ends.
Yeah.
So a set.
but
It's the set of output values. It's not really a state as such.
yeah, because all and the inputs, right? You can say that they are intermediate, but if your input happen to be, you could start by the middle, I guess.
No, but then that wouldn't count as input. Like the input is very well defined. That's
because you have the
starting out
indexes. Yeah, you're right. Because you
Yeah.
have these indexes being
intermediate values that are being computed along the way. They're part of the states, and they're represented in an entry as an entry in one of the quadruples. But
Right.
yeah. So Arthur has a solution for it. We don't know if it's a solution, but he's saying if you wanted to use the mathematics for this E0, that I'm not sure if we have actually read that, but you could do it this way. And I think that this is an exercise, but I'm not 100% sure. Okay, Jason says by input and output, I meant the equations f of mn is mn01 and f of n is n. Okay, well, yeah, so there's, it's very interesting that, this simple idea it's not that easy to express mathematically. It's sort of like taking a different kind of mathematics and a different kind of way of understanding or using math, right? But what about the Markov encoding, the strings encoding, where he says that he starts out saying this formulation of the concept of an algorithm does not include the restriction of effectiveness mentioned earlier. For example, Q might denote infinite sequences that are not computable by pencil and paper methods, so on and so on. So now he's saying if you place the finiteness requirements on this, on these 4 variables or 4 symbols, we could do it this way. And did everyone understand this? Any questions about this? Would somebody mind explaining it?
Well, I'm sort of taking it as Q is the universe that we're dealing with here. So, it could be like all numbers, could be all strings, could be stock market data, whatever, whatever that universe is. And I always like saying is like, the computer is the universe and you're the god of it.
Right, different, remember he's defining an algorithm or a computational method as this quadruple QI omega F. And so if I have computational method algorithm E, that will have one QI omega F, where Q is this particular set of things. And then if I have some algorithm G that computes some other thing, it's going to have a completely different Q and a completely different I and a completely different omega, and certainly a different F.
Okay, yeah, that's fine. But what about that additional bit of math that he has introduced to turn the computational method into an algorithm?
So it's basically doing replacement of substrings. Saying if the string looks like some stuff with this particular substring in the middle, I'm going to chop out that string and replace it with this other string. And that's the only operation that I'm allowed to do in a single step. And I have to number all of my steps. I'm only allowed n steps for some finite n. And I number them with j, starting at step 0, going up to n minus 1. And these are my steps or states. And at each state, all I'm allowed to do is say, if the string looks like this with the substring in the middle, chop out that substring and replace it with this other one.
How does that satisfy the finiteness requirement?
Finiteness requirements.
Finiteness, sorry, not the finiteness, but the effectiveness requirement. Like these operations need to be effective. You should be able to perform them effectively.
Right. Like the reader with pencil and paper can figure out, well, I can look at the characters in the string and I can find, like, does it contain this substring? And if so, I can just copy down, with the replacement. That seems pretty definite and effective to me.
Right. Yeah. So I think that, yeah, I definitely agree with that. So the idea being that, we were having this discussion about what does effective really mean, and he's given, a lot of explanation in just sort of everyday terms. But can we really agree when we are saying that this is something you can definitely do? It shouldn't be a matter of semantics or opinion or subjective thing. Like, it should be very clear that you can actually effectively carry out one of these steps, and this is one formulation of this. Anyone know of another formulation of effectiveness in terms of a formal definition of algorithms? There's a much more popular and common one. A Turing machine. Does anyone, yeah, so somebody mentioned Turing complete. Yeah, so exactly. Does anyone remember maybe somebody who's read CLRS recently? What makes a Turing machine effective in the sense of Knuth? Well, I'll leave it for you guys to look that up. Obviously, Knuth chose not to use that definition, that formal definition. But it's interesting to see, that here's one way that he's defined effectiveness very precisely and formally, and there's the more sort of common way that computer science texts and courses introduce the idea of effectiveness using a Turing machine, like how those two things map to each other. And I believe there's quite a few others. So yeah. Okay, great. So I think that we're done with the reading. As you can see, I thought that like the second half, we'd be able to focus on exercises for the entire second half, but sometimes there is going to be some stuff that sort of spills over. So let's have a look at some exercises. And the idea is that we won't try anything more than a medium level of difficulty. And even then we have to be a little bit selective because there are still quite a few exercises. But let's have a look at exercise 1, which is on page 9. And anyone want to just explain the solution to that?
Yeah, it seems to be fairly straightforward.
Yeah, it is. It's not tricky, so please go ahead.
Okay, so A goes to T, B goes to A, C goes to B, D goes to C. So I'm trying to type this as I'm, and T goes to D.
Yep, that's it. So number 2, prove that M is always greater than N at the beginning of step E1, except possibly the first time this step occurs. So for this, we'll have to go back to the Euclid's algorithm and look at what step E1 is. And then what he's saying is just prove that M is always greater than N, except for the very first time. So you can ignore the very first time, but after the very first time, M is always greater than N. So can anyone just explain why that is? We don't have to give a formal proof.
So after the first iteration, the values of M and N exchange if M is less than N. So that's why it's like that's why M will always be greater than N. Except
How do we get to step E1 after the first time?
It's after we do the exchange in E3.
And
so
what happens there?
Then N is the remainder, which invariably has to be less than N.
Yeah, there you go. So that's the answer. Yeah. M becomes N, and N becomes the remainder, which by definition is less than N. So M is always greater than N. Number 3, I found that really confusing. I just couldn't really understand what he meant by trivial replacements are avoided. And I had to look up the answer after a while. It wasn't obvious to me. Is it obvious to somebody else what the answer is?
Yes, to me. He's talking about in step E3, the reduce step, where basically all E3 is doing is renaming the variables. It's doing what in hardware we would call register renaming, right? It's saying, now do the exact same thing all over again, except this time, everywhere I say M, understand N, and everywhere I say N, understand R.
Okay, so is he then saying you're not allowed to do this renaming for N and for R?
For any of those places where I just said, like, I'm going to say do it all again, but I really mean, you know, and then you say some other stuff. He's saying you can't really do that on a machine. On the physical machine, you would either have to waste time actually physically moving the data from register N to register M, from R to N. Like that's wasting time, right? Just shuffling those bits around. What you really want to do is unroll the loop. You want to take the steps E1 and E2 and cut and paste them below E3. Well, E3 is now gone, so it doesn't really do anything, but you're going to repeat E1 and E2 3 times, changing the names at each step. So E1 and E2 stay the same, and then step E3 becomes divide N by R and let M be the remainder. And then if M is 0, the algorithm terminates, and R is the answer. Otherwise, and after you've done this 3 times, then you can go back to the first step, because now everything's back in the right registers and you can go around again.
Okay, I think that is kind of the answer from what I remember. So that's really great.
And I think I put that in.
Yeah, go ahead.
So I think I put that in the comments.
All right. Yeah. Okay, number 4, that's just calculation. We should be able to do that. Number 5, we'll just skip. Number 6. This is kind of interesting. Do we have time for this? Let's just try it quickly. So number 6, what is T sub 5, which is the average number of times step E1 is performed when N is 5? So we're fixing N. N is 5. M can be anything. What's the average number of times step E1 will be executed? And we don't need to come up with an answer. Could somebody just explain how you would do this? How would you approach this problem?
Okay, so the second time through, you would have your M and N will be 5, and the remainder from the previous step, which is less than 5. So,
which is what?
Hmm?
So what is the remainder?
A number between 0 and 4.
Okay, so 0, 1, 2,
we don't know what N was.
And 4.
So, but whatever it is, the remainder is going to be between 0 and 4, or actually 1 and 4.
Why can't it be 0?
Because it would have fallen out on step 2. If we get to step 3, then
but wouldn't step E1 have been run?
Right. So we've done that once.
Okay, so that means when if R turned out to be 0, what is the number of times step E1 is run?
Just once.
Once. Okay, so let's count that. That's for R is 0. What about the other possibilities for R?
Okay, so then we get to step 3. Saying So now m is now 5. N is a number between 1 to 4. In which case we are
Let's take the case of 1.
1.
Okay, let's take the case of 1. Let's just say that R is 1. What happens?
That we hit range of 0 next time through step 1. It's 5 divided by 1.
0, why? Why? Why would the remainder be 0?
It's 5 divided by 1.
Okay, so anything is divisible by 1. So how many times will step E1 have been run if that remainder was 1?
Total of 2.
2. So 1 plus 2, we got 3 so far. Let's go back to where we were saying that let's assume the remainder is 1. And let's say that the remainder was 2.
Then it'd be 5 divided by 2 with a remainder of 1. So that's once more and one more after that. So it would be 3 total.
3. How is it 3?
Well, right now we're...
So remainder is 2, right? Step E1 has been counted once, and remainder is 2.
Right. That gives us 5 divided by 2 gives us remainder of 1. So we've done
remainder of 1.
E1 a second time, and we already know from remainder of 1, we have actually remainder of 1 is 2, wasn't it? So after 4. No. Once more. Remainder of 3.
Remainder. Okay. Remainder of 3 or remainder of 1?
No.
I'm counting 3 for remainder equal to 2. I'm counting 3, but I may be wrong.
No, what I was saying is that
this is the sort of thing that's easier to do on paper than out loud.
Yeah, it is definitely. If you just make the columns. But does anyone does everyone have a sense of where we're going with this? Or not have a sense where we're going with this? So we've been asked for the average number of times. So average is really total number of times, or the total count that's possible, divided by how many possibilities were there. And the possibilities we're talking about are the 5 values for the remainder, 0 through 4. So for 0, we said it'll happen once. For 1, we said it'll happen twice. For 2, I said it'll happen 3 times, but I may be wrong. But so on, we can just calculate that and divide that by 5, and we'll have some number. That's the average number of times. Anyone disagree with that?
Well, what I was saying though is that on the second time through, with when we got 5 divided by 2 equals 2 with a remainder of 1, we have already solved for remainder of 1. The problem is that that solution of 2 for remainder of 1 is 1 high because there's 1 common step for everything.
Yeah, but we have to subtract 1 from whatever that solution was, right? Because for 1, right, that was count. So we don't want to count that twice because we are already in that loop. Anyway, I see what you're saying, and there could be like off by 1 errors in what I'm saying. But yeah, so that you're absolutely right. That is the idea. If you want to reuse some existing computation that you had done before, that's fine. That's more efficient. But I don't think that's really that important for this. Even if you redo some computations, that's okay as long as you come up with the answer. But yeah, so that's the idea. And yeah, somebody pointed out that this is